Alrighty, today on the Wilkin Way we're doing 10.3c, which is determining convergence or divergence, and this time we're just going to be using the ratio test. So today is the ratio test. Tomorrow we'll do the comparison test. So what we're going to do is, before we get into the ratio test, is we're just going to take a look back at what we've been doing already to determine whether or not a series is convergent or divergent. So the first thing is this one right here. This is just review. Remember that if it's an infinite series and it has a sum, then it's going to be convergent. Okay, obviously finite series don't have you don't have to worry about them converging or diverging because finite series end, so obviously they have a sum, they can't equal infinity. So we're specifically talking about infinite series here, and if they have a sum, they're convergent. If the series does not converge, it is said to be divergent. So if it keeps getting bigger without bound, it's not converging to a certain number, so it's said to be divergent. Okay, so some things that you need to know. First of all, let's take a look at this series and see if it fits any of our patterns. So what we're looking for specifically is the patterns that we're very familiar with are geometric and arithmetic, and the dot 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 implies that this is going to infinity, much like this summation notation does, and it looks like these are increasing by 1/2, but because they're alternating signs, you look like you're multiplying by -1/2 each time. So we can recognize that this is an infinite geometric. Because it's an infinite geometric, we need to take a look at r. So r is equal to -1/2. Just a friendly reminder with infinite geometric, if the absolute value of r is greater than or equal to 1, then it has no sum. This is increasing without bound. Okay, but if the absolute value of r is less than 1, then it has a sum, and we're going to use the formula a sub 1 all over 1 minus r. Okay, so for this one right here, we're going to compare it using this definition right here. The absolute value of -1/2 is less than 1. Therefore, the series will have a sum so it's convergent. So look at that. We didn't even find the sum, right? Because the question didn't ask us what's the sum of the infinite geometric series. It just said to determine if it's convergent or divergent. So in this particular case, we had to identify that it was infinite geometric. We had to identify the important characteristic from that, which is -1/2, or the common ratio, and then we also had to compare it to 1 because that's part of the definition. So that is how we're concluding that it's convergent. So if this was on a test, you would need to be defending your answer as to why it's convergent. So you would say it's infinite geometric, so I need to look at r. Because the absolute value of r is less than 1, by definition, it's convergent. Okay? Let's take a look at this one right here. 2 to the n, because there's an exponential here. This is geometric, and because it's going to infinity, this is infinite geometric. What is r? r is going to be equal to 2, because it's always the base. Remember, our formula is a sub n equals a sub gr to the n minus g, so whatever has the exponent is your common ratio. So this particular one right here, we're going to compare it to 1. And the absolute value of 2 is actually greater than or equal to 1. Therefore, the series will not have a sum. So it's divergent. So on this particular one, it's the same thing. You're identifying it as an infinite geometric. The important characteristic from infinite geometric is r. You compare r using the definition, and we find that it's greater than or equal to 1, so therefore it's divergent. Okay, the last one, let's take a look in example 1, it doesn't look like it's geometric. It looks like we're adding 4 each time. So that would make it an arithmetic. And it is an infinite arithmetic, which we haven't ever calculated a sum for because you can't. Why can't you? It's just going to keep getting bigger and bigger, and in this case it's going to be getting bigger and bigger in the negative direction. So I actually wrote plus 4 plus 4. It should be plus negative 4, right? Because that's really what's going on. So D is equal to negative 4, but that really isn't important because once I identify it as arithmetic, we know that infinite arithmetics do not have sums. They either increase without bound in the positive infinity direction or decrease without bound in the negative infinity direction because you're constantly adding a number. So infinite arithmetic series do not have limits, and I'm just putting this in here so that you can refer to it. The sum gets larger in the negative direction or in the positive direction. So that means that this is going to be divergent. Okay? Okay, well now that we have that refresher, we're going to go ahead and move on to the ratio test. So why do we have the ratio test? If you look right here, it says when a series is neither arithmetic nor geometric, there's different techniques that can be used to determine whether or not the series will be convergent or divergent. 2 of those techniques, that's all we're learning in this class, are the ratio test and comparison test. So today, like I said, is the ratio test. So what I want you to think about with the ratio test is the common ratio. And just a reminder, when we did common ratio way back in 10.3a, we said you take a term and divide it by its previous term, and that'll give you the common ratio. What you're going to notice with the ratio test is they do something similar, except for they say take the next term and divide it by the previous term. These are these statements are the same. Take a term, divide it by its previous term, right? Take a term, divide it by its previous term, okay? So what you have to do is this. So I'm going to write memorize on this, but we already know it, so it's nice if we think of it in terms of how to evaluate infinite geometric sums. So it says find the ratio. So this right here is just representing r, so you need to take a limit as n goes to infinity of the absolute value of r, which makes sense because if we're looking at this right here, we took the absolute value of r, and if the limit is less than 1, then it's convergent, much like if our geometric was less than 1, then it was convergent. And if the limit is greater than 1, then what happens? There's no sum, so it's divergent. That's what this is saying. And then if it equals 1, then it's inconclusive. But for this class, we won't give you inconclusive ones, okay? So you don't have to worry about that. And the really nice thing is that this ratio test is something that we're already familiar with slightly. So we already know that if r is less than 1, it's convergent, and if r is greater than or equal to 1, it's divergent. Okay? So because we're doing the ratio test, we have to do the absolute value just like we did when we were doing infinite geometric and we took the absolute value. Okay? So let's go ahead and take a look here at example 2. Before we do that, just note that it's generally used when the series involves powers or factorials or contains products of consecutive integers. Okay? So example 2 says use the ratio test to determine whether each series is convergent or divergent. So in order to do this, we need to know what a sub n is and a sub n plus 1. So always start with a sub n, it's just easier to do. So if I do a sub n equals. Do you guys notice that this is alternating signs? And in yesterday's lesson we learned a really easy way to write alternating signs is -1 to the n. So that takes care of that. Well, what's happening in the numerator now? So clearly this is not geometric or arithmetic. Remember, that's the purpose of the ratio test, is when it's not geometric or arithmetic, you can find whether or not it's convergent or divergent. So what I'm noticing up here, maybe not necessarily at the beginning, but this is increasing by 1 each time. So I'm going to write 1n because that's how we do arithmetic, so I'm just actually going to write n. And I know the first two numbers don't fit this pattern, but I'm going to try and see if maybe there's something else going on that's going to make this work out. So I'm just going to leave it n for now. And then in the bottom, if I look down here, and again, it's just a tip to sometimes look at the later terms, I'm seeing it's increasing by 2. So that would be 2 to the n. Okay. So that fits. If I plug in 5, -1 to the 5th power is negative. It is negative. That's 5. And what's 2 to the 5th power? It's 32. So that definitely works for the 5th term. Let's see if it works for the first term and the second term, because those are the ones that didn't appear to fit the pattern. So I plug in -1 to the first term, and that's negative. And then this is negative, so that's good. And then that's a 1. And what's 2 to the n? 2. So it does work for that one. So that's a sub 1. Does it work for a sub 2? So I'm just going to do the math up here so you can see what's going on. We have -1 squared, which is good because it's positive. And then we have to multiply it by 2 all over 2 to the n. Or sorry, 2 squared. So -1 squared is 1 times 2 is 2, which is 2, and 2 squared is 4, which is 1/2. So of course mathematicians wouldn't write 2 over 4 because then it wouldn't be reduced, but in fact this does meet the pattern. Now the other one that we need is a sub n plus 1, which is super easy to find. Everywhere there's an n, you're going to change it to n plus 1. So a sub n plus 1 equals -1 to the n plus 1 times, there's an n here, I'm going to write n plus 1 instead, all over 2 to the n plus 1. So there was 3 n's and I changed them all out for n plus 1's. Okay? Why do I need to do that? Well, that's because the ratios test says take the limit as n goes to infinity of this. So I'm going to show you guys on a post-it. Don't write this down, but because I'm going to show you a shortcut. So this rule says take the limit as n goes to infinity of a sub n plus 1. So I'm going to take a sub n plus 1 right? That was a sub n plus 1, kind of hiding under my post-it over here. And then it says to divide it by a sub n. Oh, that makes sense because that's how you find the common ratio. Take a term and divide it by the term before it. Cool. Well, what do we end up having here? We end up having a complex fraction. So how do we get rid of complex fractions? We copy dot flip. Well, guess what? In all of these limit problems, you're always going to be doing copy dot flip. So rather than having to write it in this form every single time, it's just going to be easier if we take our first step and make it the limit as n approaches infinity of copy the first one times, and I'm going to reflip that, reflipical. So that is 2 to the n all over, oh, nope, not 2 to the n, yep, 2 to the n, sorry, all over -1 to the n times n. And it's still absolute value, that's based upon the definition. So that was copy dot flip there. So this is what we have. So now what our job is to simplify this. And this one is actually n plus 1. How did I miss that, right? So I just didn't copy it properly. So next what I'm going to do, so I'm just going to write down here what I did. So this was copy dot flip. That's all that step was. So in the next step, I'm going to simplify exponents, which is sometimes hard for students. So I'm going to show you guys what exactly I'm doing on a Post-it as well, just so you can see. So remember properties of exponents? They say this, like if I have 2 to the third over 2 to the first power, this equals 2 to the second. Well, how did I get to that? I went 2 to the 3 minus 1, which is 2 squared, right? Or what if it was flipped? What if I had 2 to the second over 2 to the 8th? I know you guys know what this is without having to break it down this way, but this would be 2 to the 2 minus 8, which equals 2 to the negative 6, which is equal to 1 over 2 to the 6. So I want you to keep those properties of exponents in mind while we simplify this problem right here. So I have negative 1 right here. That's my base, and that's my base. And here are the exponents. So if I do negative 1 to the n plus 1 all over negative 1 to the n, because they have the same base, I can subtract the exponents. So that's n plus 1 minus n, which equals negative 1. The n minus n cancels out. So I have negative 1 to the first power, which is just what? That's just negative 1, okay? So when I go to do my next step, again, I'm simplifying in the absolute values. I'm going to have negative 1 to the first power, so that's all stemming from that right there. And then n plus 1 cannot simplify with n. Remember, you would be, a puppy would be dying because you're trying to cancel out common terms instead of common factors. If I wanted to cancel out anything involving n plus 1, I'd need the exact same thing in the denominator, which I don't have, so that's going to be n plus 1. And now I'm moving on to 2 to the n. So back to my Post-it to show you this. 2 to the n is here. And I have the same base down here. It's over 2 to the n plus 1. So now, subtracting exponents, I'm going to be very careful. Anytime there's more than one term, I'm going to put it in parentheses. And then I'm going to distribute. So then that equals 2 to the n minus 1, which equals 2 to the negative 1, which equals 1/2. Okay, so that's just property of exponents. So where is this 2 going to end up? It's going to end up in the denominator. So I have 2, and then here's that remaining n. It kind of seems like it's confusing, but really it's just property of exponents. So I'm going to put a 1 here. Nope, not there. Sorry, guys. I know it's property of exponents, but so just be careful with those is what I'm getting at. Okay, so now that I'm completely simplified, what I want to do is see if there's any, remember with limits, if there's a constant, we learned that you can pull it out in front. So if you look at this, negative 1 to the first power is negative 1 over 2, so that's like negative 1/2, but there's absolute value signs here, so I'm going to pull it out by evaluating the absolute value. And what I have left is n plus 1 over n. So that 1/2 came out in front. Why did it become positive? Because I took care of the absolute value signs, which is why there's not absolute value signs here. So this was properties of exponents. And on this one right here, this was pulled out constant and evaluated absolute value. So that's why those signs are no longer there. So you don't want to take care of the absolute value till you're fully simplified. Okay, look at this. This is yesterday's lesson. How do I handle that right there? So that's 1/2. The limit as n approaches infinity of n over n plus 1 over n. So because there's only one term in the denominator, I just do a little whoop whoop. And then that is going to be equal to 1/2 the limit as n approaches infinity of 1 plus 1 over n. So here you need to be careful because we're still writing the limit until we evaluate the limit. So the limit of a constant is the constant. So I have 1/2, which is out in front, and now I'm going to evaluate. The limit of 1 is 1, and the limit as n goes to infinity of 1 over n is 0. So that equals 1/2 times 1, which is 1/2, which is less than 1. So our common ratio is less than 1. So therefore, by the ratio test, so this you do have to have in there because you're defending what you just did, the series is convergent. Okay? So it says use the ratio test to determine whether each series, so you're just, when you're doing your final conclusion, you're just repeating the statement that was made here. So 1/2 is less than 1, super important to compare it, so therefore by the ratio test the series is convergent. So I did all that out there for you like that, highlighting like these. This is a super key part to it. You have to have that that statement right there. Okay? Okay, on to example 2b, so it's going to be the same thing. The really nice thing about this is that because we weren't given in series form where it's listed out, we already know what a sub n is. That right there is a sub n. So obviously not with the summation sign, but that piece is a sub n, so it makes it really easy for us to find a sub n plus 1 because we're just going to go -1 to the n plus 1, 3 to the n plus 1, all over n plus 1 squared. So that's nice. So we can get started right away. So we need to take the limit as n goes to infinity of the common ratio. And technically these don't have a common ratio because they're not geometric, so I'm just going to say ratio. So we're taking the ratio of the bigger term always, a sub n, the next term, divided by a sub n, but because we want to save ourselves time, and we know we always do that, we're going to just copy dot flip in our very first step. Okay, and then our next step is to simplify. So you're looking to simplify any way you can, but let's start with exponents. So -1 to the n plus 1 and -1 to the n, just like before, we would subtract those exponents and end up with +1. So that's going to go there. We have 3 to the n plus 1 and 3n, so I'm kind of just working across my numerator to start. 3 to the n plus 1 and 3 to the n. This one's kind of nice because we'll actually end up with more in the numerator, whereas last time, do you see how we had 2 to the n over 2 to the n plus 1? The n plus 1 was in the denominator, so that's what gave us the 2 in the denominator. But this time, 3 to the n plus 1 and 3 to the n, when I subtract those, I'm just going to get 3 to the first power. And then I have n squared because I will not be a puppy killer and I will not try and cancel or incorrectly shower the power or anything like that. Okay, so after we simplified, we did properties of exponents. We do properties of exponents, then we simplified, and now we need to pull out the constant and evaluate the absolute value. So this is -1 times 3, which would be -3, but we're going to do the absolute value. So once we, again, do the absolute value, you can't keep writing absolute value because you already took care of it. So this is n squared. And I'm going to FOIL this so that I can work with this. So I FOILed that. Okay? And then what do? Same thing from last lesson. So because there's more than one term in the denominator, I'm going to divide everything by the highest power of n. So this is n squared over n squared And then what am I going to do here is I am going to go ahead and simplify all those fractions I just created. So I get 1. And that's right there. Now what I'm going to do is evaluate my limit. So I'm going to have 3 times the limit of a constant is the constant. Limit of a constant is the constant. Now this right here, I'm going to put a little side note for you just so you can see how this works. So this is like 3 times the limit as n goes to infinity of 2 over n. There's a constant there of 2, so I'm going to pull it out in front of the limit. So I have 3. And yeah, that's 6. I know, I'm just trying to show you. Okay, so that goes there. And so then that's going to be equal to 6 times the limit as n goes to infinity of 1 over n, and that's just 0, so 6 times 0 is 0. Okay, so I don't need to do all that work over here. If it's 2 over n, it's still going to be 0, so I'm going to leave it as 0. So that gives me 1 divided by 1, so that's multiplied by 3, which is greater than 1. So therefore, by the ratio test, I'm just abbreviating, what do we conclude? The series is divergent. Okay, so as you're going through those notes, if you have any questions like, hey, well, how'd you go from one step to the next? Make sure that you mark a little note and write down your actual question so that when you come to class you can ask me about it, okay? Let's go ahead and flip it over. Here we go, example C. This one involves factorials, so let's go ahead and take a look. We have this right here is a sub n, so that's so nice. And what's a sub n plus 1? So we're going to have n plus 1 factorial. Ooh, this is going to be super interesting. Be careful with your math here, okay? First of all, put the n plus 1 in parentheses because you're going from 1n to 1 term to 2 terms. And then we're going to simplify this. This is 2n plus 2, right, when I distribute. So that's going to be 2n plus 5, and that's all in parentheses and has a factorial. So there's n plus 1. So how do we start these? The limit as n goes to infinity of the ratio of the bigger one, n plus 1 factorial, all over 2n plus 5 factorial, times, we're going to copy that, flip that, obviously you need the parentheses around those things right now. Okay, now we don't have to worry about simplifying exponents, but we do need to worry about how to simplify factorials, and we did this in a previous lesson. In fact, I think it was 10.1. So this one is bigger than this one, so we're going to write this as n plus 1, and then that's going to be n factorial. So that means the same thing, I just subtracted 1. And then up here, I'm going to leave this as 2n plus 3 factorial, because down here, this one's going to be bigger. And so I'm going to choose to write that by subtracting 1 each time until I get to 2n plus 3 factorial. So that all comes from that piece. So this is just another way to write this right here. But I still have this n factorial. So now I'm going to simplify. Bam, bam. Those are actually common factors because I'm multiplying, and those are there too. Now, the next step here too, we're going to evaluate the absolute value. There's no constants to pull out, and there's no negatives, so we actually are just going to drop the absolute value. So in the numerator, I have n plus 1, And then so I don't have to keep doing more and more steps, I'm going to multiply those out. And I get 4n squared plus 18n plus 20. Then I'm going to divide by the highest power of n because I have more than one term in the denominator. Please pay attention to the fact that every single time I'm writing this limit, so again, I don't have the absolute value anymore because I evaluated it, right? Here's my little quotation fingers. There's no negatives to make positives, so I'm good there, and there's no constants to pull out. What I do want to say is for some of you, you'll need to do this step every time, but I want to show you guys that there is another way to do this if you can handle it. And see if you just can process this. So the other thing you can do, we know the highest power of n is n squared, is write it like this. So what you're doing is multiplying everything by 1 over n squared. So I'm multiplying all of that and that. So these two, this statement and this statement, I'm doing the exact same thing. But instead of having to write n squared 1, 2, 3, 4, 5 times like I did here, I only have to write it twice. Make sure you don't write times n squared because we're dividing everything, so we can just write 1 over n squared. Multiplying by 1 over n squared is the same thing as dividing by 1 over n squared. So now I'm going to simplify that, and I get the limit as n goes to infinity of 1 over n plus 1 over n squared all over 4 plus 18 over n plus 20 over n squared. Now I'm going to evaluate my limit. So I'm going to get 0 plus 0 all over 4 plus 0 plus 0. Remember we talked about how that number up in front isn't going to affect it because you're going to pull it out in front and then it would be 1 over n, and that limit is 0, and then times the constant would still be 0, which is 0 over 4, which is 0, which is less than 1. Therefore, by the ratio test, the series is convergent. Okay, so that's how you do that one. Now I'm going to offer 1% extra credit for those people who can actually do example D, and I'm going to give you a little help right now. So you have to write the pattern for this. The first thing, anything that doesn't have a denominator, give it a denominator, and you can see in the numerator you're increasing by 2 each time. So we learned that that's an arithmetic, so a sub n would be 2n, but because the first term when I plug in 1 isn't giving me 2, it's actually giving me 1, I need to subtract 1 to get to that. Obviously you guys can see that there's factorials going on here, but how the heck do you write that using n? Well, what you're going to do is look at the last numbers because that's really important. So what's happening with those? Those are going up by 2n. So you're adding 2 each time, right? Do you see that? So that's 2n. But when I plug in 1, my first term isn't giving me 2, it's giving me 1. So I'm going to subtract 1. And then the last thing I need to do is put a factorial on it. So this is the 1, 2, 3, 4th term. So look, what's 2 times 4? 8 minus 1, which is 7. So that's 7 factorial. So you just need to go ahead and finish that up. You need to find a sub n plus 1 and do the ratio test. And if you have proper notation and get it correct, then you will get 1% extra credit on Monday. Alrighty.